Good morning, everyone. My name is Vansh Agrawal, and today I will be presenting my project, Coarse-graining the 2D Ising model with a simple neural network. Now, the main goal of this project is to train a neural network, whether it be a small multi-layer perceptron or a CNN, so that we can understand the coarse-graining map that was used in various physics models. Now, today we will be doing this on a 2D Ising spin model, where our input will be a 32 by 32 grid with various spin values ranging from -1 to 1, and the output, uh, which is a coarse-grained lattice going from 16 by 16. Now, our main goal here is to check whether properties such as magnetization and such are preserved here or not. So let's move on. First, let us understand why this matters and what the essential contribution of this project is. Now, first we understand what AI interpretability is. As we all know, uses neural networks, which are generally considered as black boxes, where we do not know what the internally model has learned, but we try to figure out through the medium of AI interpretability as a study, where we specifically look at activations and we run specific tests on them to check whether these models have a certain type of behavior. Now we can extend this to maybe LLMs, where if you take ChatGPT, for example, if I put in a specific test, such as a sparse autoencoder or some other sort of a network in between, to test what sort of activations these functions are outputting. So, for example, we can check whether a model has specifically learned malicious behavior through this medium, where the sparse autoencoder will specifically activate those activations where the model is behaving maliciously. So this project aims as a first step towards this, where we try to use a 2D Ising model, which where there are various physical properties that you have to keep in mind while doing the course training. Here, course training is a process where you have to keep in physics bounded rules, and these rules are something that the neural network will have to learn on its own. So, from this, what we understand is that this can be used as a good measure to check how much a neural network has learned and check its inductive bias, whether this neural network can learn in certain number of parameters or with a certain number of training data. Here, the course training overall formalizes what we preserve in a AI model. And if we extend this project further, we can even go for to remove features and activations which are harmful or unnecessary for our networks. Specifically, given that deep learning is at a stage where there is a huge amount of compute required, and if we are able to remove parameters and features, that serves as a very good basis for progress in AI in general with the use of physics. And this project also has a very educational purpose. It's in the sense that it's very simple to understand what's going on while essentially showing these concepts that require. So first, let's understand the basic physics concepts that are used here. We know that an atom has a spin up and down. So Ising model, a 2D Ising model is a simple configuration of atoms where the spin has only, where the main property that we look at is the spin, which can either have the value -1 or 1, showing up or down spin in a square lattice. Now, for this system, the most important property, as we know, is Hamiltonian, which there represents the energy that this system overall loads. J is the constant that we consistently keep, but the SI and SJ are the ones that we just discussed, are the spins of these modules. Now, how do we decide how much energy this is? As you can see from this equation, what we have to check is the nearest neighbors. Only nearest neighbors interact in this model. So the atom can only interact with the adjacent atoms that it has. And the boundary conditions here are simple periodic conditions where there is an atom at every interval in the 2D space altogether. So now what we have to check is how can we generate these how models at all. So before that we go into, as you can see, this is something that our lattice looks like for the 2D Ising model, where some of the spins have up and some of the spins have down. as you can see, certain spins have adjacent up, up, while some have up, down adjacency. Now, what this decides is the ferromagnetism or a paramagnetism of a material. If, as you can see, that in below critical temperature, which is Tc, the ordered domains, it remains in ordered domains, and there is high magnetization. That is, that all the spins are pointed towards the same direction. But in above, in high critical temperature, what you see is that there's a lot of disorderedness, and there's a lot of because of that, which causes low magnetization. So what now we check is that what happens at critical temperature, and we see that there is scale free fluctuations, and there's large correlation length as well. That is that far away atoms interact with each other as well. So now coarse graining. Now we'll move on to what essential gross graining is. Gross graining is a process where we reduce resolutions while retaining all the essential physical properties. Now, how do we do that in general cases such as this molecule? As you can see that the molecule here is very complex and it has a lot of ups and downs in the structure and signature that it has. But if we apply the process of coarse grading, which is pretty much smoothing out the curve or smoothing out the process uh, s- uh, blocks that you have, you can see that our molecule here is overall simplified where we have replaced with this yellow atom. And our overall properties now you can are much more smoother, and the essential areas such as this valley here and the red dot, all of that remain. So what this allows us to do is that this allows for high calculations, heavy calculations with a lot of numbers and a very high value to be reduced down into a simpler system which can be processed much quickly and while giving the same properties that it has. So in our example, we will be looking at 2 by 2 blocks where these 2 by 2 blocks are converted into one spin. So these four atoms will be merged into one spin with a simple rule of majority and average, as that is a simple step for our project right now. If we want, we can look into higher post-grading techniques and check our inductive biases there as well, and that can serve as an extension to this project overall. Now, fewer degrees of freedom means there will be more similar macro state, but you still get the flow of effective theories there. And there's a link to the regroup theory that we have. Now, what we move on to is the AI plus physics part of it. This coarse grading operation is generally done through some operations and some sort of manipulations that exist in the system. But with this project, what we aim to simplify is that instead of using some hard-bound rules, the network itself can learn these course prediction rules. And further, if there are emergent properties which we do not know of, whether AI retains these properties or not, or whether these are lost while course grading. So our learned maps will be from 32 by 32 to 16 by 16, and our ground truth has been created using a block majority slash average coarse grading, which is a much simpler form of coarse grading that we take. And our target properties are whether the domains are preserved, whether there is magnetization, and whether the correlation between the atoms still exists perfectly. And for this, we will specifically show the model, the matrix, and visual comparison. First off, let's look at our data generation process. Now, our data generation process has been carried out throughout the Metropolis Monte Carlo simulation, which ensures a diverse and representative data set for our learning. Now, let us look at the process. First, we start and we define the size of the shape that we want, which we have given at 32 by 32. Temperature, which we have kept at various temperatures so that we can check how the model is behaving at critical temperature, above critical temperature, and at critical temperature, and the shape of the overall system. Now, let's generate our random matrices, which will go from either 1 or -1. Now, after that, we check whether the energy is below zero. If it is a yes, Then we go and flip the spin. And if the randomly selected object that we have taken has an e raised to the power minus uh, delta e by t less than as with less than that, then we get a flip spin. If both of these conditions are not satisfied, then we don't flip the spins. And after once this process has been entirely done, we return the matrix and we collect the data to get its energy, magnetization, specific heat, and susceptibility, etc., etc. Right? We have represented this condition using a formula which is called the Metropolitan-Hastings formula, which uses a acceptance rates P equal to minimum one E minus energy of the two spins divided by T. And we sweep across all the critical temperatures. So this ensures, now we will show this on our code. So this is the code base that we have used. And this is, here we have saved all the result. The models can be used as well, so there's no need for retraining. Figures contain all the results that we have. Now, as uh, shown, here are three example configs that we have. This is a temperature below critical temperature. As you can see that this is very highly ordered and all of the spins point towards the same direction. But if we look at this one, here as you can see that it is much closer to critical temperature and there's higher uh, disorderness. And we can say it's similar for this. But here as you can see there's much more correlation and there is much more red. That is the -1 values are much higher than the +1 values. So we can expect that this system would be close to critical temperature. And as we have done in our code, which you can see in datagen.py, that our code ensures that there are three specific uh, magnetizations that we want. That is high magnetization, critical and low magnetization, and intermediate phase. So once we start generating the data, as we can see, first we have defined our critical temperature, we have defined our temperatures range that we will take. And then we start generating using the simulator that we have created in here. Here's the class that simulates the entire thing. J is the coupling constant, as we discussed, and H is the external magnetic field. To calculate the energy change, as you can see, this is the following formula to get the neighbor sounds, where we take the spin of the one just before this and this current spin, and then the spin after, and so on and so on, so that we cover all the four directions and we get the neighbor sound, which when then multiplied with the constant and multiplied with the current spin, we get the delta E. Using this, we can calculate all the formulas that we require. So once we have our calculated we can take the multi-quantum step where we attempt random flips and n is the total number of spins, n random flips and n is the total number of flips, as you can see from this part of the code. As then further, we also look at how we are calculating the magnetization and energy right at then and there. We have got our magnetization, which is sum of all the spins by psi square. And similarly for energy, we use the formula that we showed in the previous slide. Now, once all these uh, configurations are generated, we save them all in a isingdata.npz and a .pkl file, as they are very easy to access using NumPy in our later scripts, which we can check in trainmodel.py. But before rushing ahead, let's move on to the slides again. So as just demonstrated, we see the acceptance criteria for how we can simulate Ising models and create synthetic data, making it very easy to reproduce this experiment using succeed. This is one of the figures that we showed to you in the code example. And now we have created our ground truth course grains, which can be used to learn the model. Now, The exact coarse graining rule that we use is that the new spin is determined by the majority sign of 2 by 2's block, and the dice are resolved by assigning 0 or a random average value. An alternative method involves averaging the values first and then applying the threshold at 0, but it really does not make a difference to the variance that we'll have. Now, the data set splits that we have kept is 70%, 15%, and 15%. And the input size is 32 by 32, output size is 16 by 66. This allows us to use two models, multi-layer perceptron and CNNs. So for that, first we will explain what exactly multi-layer perceptrons are. So if we take an image, a 32 by 32 Ising configuration that we have, it will have certain values here. This can be 1, minus 1, 1, minus 1, anyways. And these are the first input layer that we have. This input layer is connected to all the nodes at the next layer, where this is decided by summation of all these values with a weight, where the weight is represented by these arrows. Once we sum all of that, we use an activation function called ReLU function, which adds a nonlinearity to our neural network. What a nonlinearity ensures is that we can learn any type of function. If this nonlinearity does not exist, we can check that the equations that get formed, that is f is equal to wx plus b, is always going to be a linear equation as the next input is also linear, and we'll keep on inputting this, which gives a linear of a linear equation as a linear equation altogether. So this activation function here is one is called ReLU function, and it simply does is it clips the values below 0 to directly 0, and all the values above 0 are retained as it is. Once these values are there, we use them in the next layer as well, and then the next layer. These are overall called the hidden layers where the computation happens, and we do not take care of that. This is the values, exact weight values, the arrows that we know, are calculated using an algorithm called backpropagation. Backpropagation takes the loss of the actual value. Say it gave the probability of this image as airplane as zero point 0.5 and this as 0.36. But we want our network to be more confident in its prediction assumption. So what we will take is that we will put these values as 0, 0, 0, 0, 0 until we reach shift where it will be 1 and then 0. We calculate the difference and then sum all of that, and we get the loss value. This loss value is then propagated throughout the network using the property of chain rule, where we check that the dependence of this value, changing how much of this value will lead to a change in this value, and accordingly change our weights, which will result in optimized weights to get absolutely confident values in the end for our prediction. So we can do the same for our coarse grain network where we'll flatten the values, we'll keep three layers in between and an output layer outside as we can check in our training setup. Now, the problem with this setup is that there is no spatial correlation. That is, for a neural network, a pixel at the left corner and the pixel at the right bottom corner is the same, and the distance does not matter to it. For it, 0.0, 0.3 and zero point 0.2 have the same distance as 0.3 and zero point 0.4, which is generally not the case. And this spatial information is very important to in images and various physical networks that we have. For that, we use a small CNN, CNN, which is called a convolution neural network, where we use these convolution-like filters which are passed throughout the input and then uh, which are passed throughout the input and pulled into a smaller output. And once we have these feature extracted, we can get that to a normal fully connected layer as we saw here, and then we can output. So for this, if we check, this is how a convolution process looks like. We have the layer, and this is the image. There is element-wise multiplication, here 1 into 1, 0 into 0, 1, 0 into 1. And then they are all added into the output section. So this would this would be the grid for this 4. The middle part would be the grid for this 3, and this would be the, as shown in this diagram, would be the grid for this right 4. And we repeat this step throughout with various settings, with changing the padding, that is adding extra values to the layer at the side, or kernel can change, where we can take higher kernel sizes or lower kernel sizes. And stride, which decides how much does the kernel shift. Does it shift only 1 pixel, or does it shift 2 pixels at the same time, which results in the output of 2 by 2. Now, which results in the output of 2 by 2 in this case. So here in our project, we specifically use a smaller convolution layer with the small kernels 3 by 3, as our objective is to check the inductive bias of these natural models itself. So first we downsample and we use normal striding conversation for in our tooling. We use normal and we use ReLU activation, which we discussed already. The optimizer that we use is Adam, which is Adagrad plus momentum, and the learning rate is 1e minus 3. The Adam optimization is the most suitable for our scale and for our purpose, as we are not working with a very large network, which requires the necessity of using newer optimizations of Neo1 and such. And our batch size we have kept as 128, and because this is not a very large network and this can be very easily run on a GPU on our own local setup. We have kept this light dropout as well, which is the process of removing certain weights and activations randomly throughout the network so that there's diversity ensured throughout the network. And the same representations are not learned in all the nodes. So covering that up, we look at now we decide the baseline that we have kept. There is an exact block majority as the ground truth that we have created, and MLP just directly flattens the input into a dense layer, and we have kept the main CNN as the comparison for the baseline for the MLP. Baselines are used to contextualize and give lane and clarify versus what's learned versus what's trivial. The evaluation metrics that we have kept are the magnetization values and the error there, the correlation that has been observed in the entire physical system, the spin accuracy that is outputted in the coarse grained map, and in the reconstruction, and the which is calculated using the mean square error or binary cross entropy loss if needed. But here we have specifically only kept mean square error. Just to ensure what binary cross entropy loss is, what mean squared loss is that we take the actual value minus the predicted value whole square and summation of all the losses. And this is what we get as the value of the mean squared error loss. The price binary cross entropy loss uses the formula P log 1 minus P with logits as its output, because this is a good loss which has been proven in specifically classification tasks. Now, we also have the option to consider hybrid losses, where such as using magnetization penalty, but that there deviates from our objective, where we have to specifically check whether the model can retain its magnetization without uh, adding that loss to the without adding that penalty to the loss. Now, let's just move on to the code before we move on to the results. So as you can see, this is our training pipeline. First, we load the data with a simple data loader. As we said, the PKL files and the metadata file will be required for our. For, now, first, we split the data into the split that we talked about. That is 70, 15, and 15. All right. Yeah, here. So our test size is 20% and our validation size is 10%, as we already discussed. And our main train size is 70%. Now, once we have our samples adjusted and created, we move on to the actual CNN model. Now, for this, we have the course break, the models.py file, where the actual model configurations have been set. The Ising data format has been first defined using simple torch tensors and the dimensions as well. Then we use our main CNN. As you can see, there are three specific convolution layers with all kernel sizes 3 and padding as 1. And then we use a simple pooling layer who to get the desired output size. Now, the purpose of pooling layer is that using after convolution, there's a lot of unnecessary features that are still left in the network, which can be simplified using a simple 2D pooling layer, which does averaging of all the values, or whether that be max taking only the maximum values out of the kernel. So that is our pooling layer. And then we have the final output layer. After that, we also do batch normalization, which ensures that the training batch that we have has is not very erratic. That is, outliers do not affect the training very harshly. So there's only in small changes that are coming from these larger samples, and for that we use batch normalization, which reduces all the values from zero, which uses statistical normalization to normalize values from 0 to 1. Now, and here is a forward pass. As you can see, that the activation functions that we've used are ReLU functions. The ReLU dropout, then second ReLU, then dropout, then ReLU again. Then we have the adaptive pooling layer, which we just discussed, and then the final output. As you can see that here the activation function specifically has been chosen as tan H, which instead of a normal ReLU, which has a range from 0 to infinity, here the range is limited to -1 to 1. Now, and this is the specific, uh, this can be used instead of sigmoid function as well, which is equivalently good for our classification task in the last layer. Now we go check out our MLP layer. Now our MLP layer has only a certain hidden dimension size that we have defined in our configs in train model.py. But as you can see that these are the hidden, this is the loop for hidden dimension layer, which we have created with batch normalization and dropout of 0.2. That is 20% of the weights will be removed from the layer every iteration of train. And finally, we have our trainer, which which both the models use, where our main backpropagation algorithm has been used up. The learning rate and the weight decay has already been defined, and we train this R networks here specifically for 10 epochs, which we can check out on train models.py. All right. So moving on to the results. Our repo also consists of a proper project summary and report, which tells you about uh, what exactly has happened throughout our training process. So as you can see, first we talk about the temperature scaling, which we talked about the diversified samples. So there is 200 samples for each temperature. So this is ordered ferromagnetic 0.5 temperature Kelvin, and then there's 4 Kelvin, which is highly disordered, and there's 200. And then there's the ones which are near the critical phase at 2.5, and all of them have 200 configurations. And the split, as talked about, is 70, 10, 2020. One of the features of this repo is that this is GPU accelerated. So this uses all the CUDA features that you have, ensuring faster training and good and optimized training. And the loss function has decided we have used as mean squared error. There was no need to go for bucking cause and tribute loss as this is not specifically a classification task and more of a regression task where you have to predict the values. And MLP layer also has just be shown. Now, we look at the training history, and as you can see that the loss has smoothly gone down in both validation and training. But we cannot say the same for the MLP because, as you can see, the MLP's loss does not decrease after the 10th epoch up till the 50th epoch, whereas there is a drastic change from the 10th to 50th epoch in the CNN training history. There's overall slower convergence, and the validation loss is also 800 times worse than the CNN. And this we can specifically see that if we look at the number of parameters for both the networks, here we have only trainable factor parameters as 10,000, around 10,000 parameters. But for the multi-layer perceptron, we have around 300,000 parameters, and yet it still performs the worst. We checked out the further properties that we had discussed in our evaluation process. First, the test MSE. As you can see that it was much worse in the multi-layer perceptron, and, and the mean absolute error as well was much worse, while having 32 times more parameters. How the behavior works. If we want, we can also check their actual properties. So first, let's look at the MLP training history. As you can see that the loss and the training was smooth in both CNN and the MLP trainings. And there was not a lot to differ, except the fact that the loss for the CNN went much lower than the MLP. Now, as we talked about the sampling that we have, you can check that the magnetization changes over various temperature ranges. And here's the critical temperature that we have, which can be seen here as well, where we check the density of the magnetization or throughout the systems we have, that density versus magnetization. And here is the coarse graining preservation, that the magnetization for both are similar to what our coarse grain preserved network has produced. And here are the examples of our coarse grain. Here are the input examples that we wanted. Now, let us look at the predictions that these neural networks have done. So, as you can see that the CNN and the MLP difference, there's not a lot to decipher here because here the sample one is in an ordered state. But let us look at our sample two, which is a critical or a disordered state. And as you can see that there's the target and the fine grained version. The CNN is very close to what we wanted, but the MLP is not able to retain any sort of structure at all in its predictions for a critical or disordered state. And here, as you can see, there is some sort of structure that the MLP tried to learn. So there was some sort of learning happening that we can see. But the prediction quality is still much worse, and there is the properties that we wanted have not been preserved at all. And we can see this for even other critical and disordered systems. This is for another ordered system where all the spins are up. And here the MLP prediction is closer to what we wanted, but irrespective, in the middle cases, it was much worse than expected. So as we can see, let's look at the physical properties that we wanted. Now, as you can see, that the coarse-grained magnetization that the neural network had predicted was very close to the fine-grained magnetization itself. And this goes for the distribution as well, where the density versus magnetization distribution the error is very small, ranging from worst from 0.15 to 0.010. And the same we can go for spatial pattern preservers for the CNN. So overall, what we can highlight from this is that this gave us very successful results in our demonstration, where we have checked out that the CNN performs much better than the MLP. Now let us think about the reasons why this might be the case and how exactly this has taken its form. Right. So first off, the magnetization RSME in the CNN is very low. That is, the correlation with the ground truth is very good, and even the spatial pattern has been preserved throughout this. So as you can see that the CNN has perfectly learned the global properties of the system, of the Ising model, of how it behaves, as well as how the local spatial correlations need to be preserved throughout the model. Whereas the multi-layer perceptron, the MLP model, had failed to do this and had failed to do this. Now, the main interpretations of such result is that while we can think that block averaging is a very simple and deterministic method of coarse graining, the simplicity achieved allows us our CNN to actually show the difference in the inductive biases that it has compared to the normal neural networks, where the local operation of convolution and pooling proved to be much more effective at learning the operation than using a neural network which uses a much more which has no spatial correlation. And there is no symmetry or translation invariance. That is that the physics of Ising model is the same everywhere on the lattice. And the CNN's shared weights, that is the convolution weights that we learn, exploit the symmetry and allow it to learn the same filter throughout the entire lattice. Now, what this demonstrates is that a standard neural network can learn a specific physical meaningful abstraction from data, that these physical properties that exist in our real world can actually be converted to can be learned by the neural networks. If we go for higher uh, level of coarse graining as well, we can do a similar test whether such a network can learn this sort of coarse graining or not, which proves the inductive bias in these networks itself, and while as well as proving whether the physical properties such as magnetization have been retained or not. Now, as this, we also prove that the parameter count do not matter, that the architecture itself matters more than the mathematical, than the uh, compute you have. So, this CNNs perform better on Ising models specifically because there is spatial correlation. So, if we look at more physical models, more problems in physics, we have to accordingly decide according to the physical properties it has, so that it can learn these real world properties much quickly than a standard neural network or something like that. And then the more uh, research direction that we can find for this is that we can use that if we want to simulate higher level, bigger lattices, and if there are certain other physical constraints, we can use physics-informed neural networks or differential networks, which can ensure that these physical property constraints have been already added to the loss. Now, how this matters for beyond Ising. As we talked about the materials, we can also look into climate and turbulence, where the subgrid parameterization can be learned by a simple network such as CNN, proving that we can even have real world impact with it directly. Thirdly, we also show compression, which is physics preserving model reduction. That the data can be compressed while having its physics properties reduced with the help of AI. And interpretability, understanding how these inductive biases uh, exist in the neural network. Now, as we have talked about, that there's concrete abstractions, there's coarse graining is measurable and visual. Feature understanding that filters align with more physical heuristics and the real world properties of magnetization. And physics priors that localization matters more than the scale of data you have, right? So now to understand uh, what this repo mainly consists of, first we look at our data files. So the data has already been saved, so anyone can just simply go and run the train model.py, which will start from the data that we already have saved, and we already have saved models as well, which can be used. Further, there are summary metrics and model comparison files as well to quickly distribute and understand the data that we have and how the training process throughout our experiment. Now, looking forward, as you can see that I have provided simple instructions to set up. Either you can use pip install or you can use the UV library and then use UV sync to set up your environment. Then simply generate the data, train the model, and then models will be saved in the models. There will be figures for all the visualizations required, and then there will be results for more structured interpretation of what we have produced. And with that, the educational value that we provide is that we explore phase transitions in condensed matter physics and how Monte Carlo simulations can be used to create data for actual physical networks. And how AI can play a part in uh, learning representations and reducing the parameters and information dimensionality altogether. And we also proved that convolutional networks work for best for the spatial data and use the loss function for the regression problem that we know. Now, extension and future works onto this. We have also provided the suggested hypermine parameters that we wanted in the slides itself. Further on, what we can add is that there can be probes which are autoencoders which take data at a lower dimension, throw it onto a higher dimension, and then compress it back to a lower dimension for further processing. What this allows is that once the data is at a higher dimension, there is more values, more uh, representations that can be separated rather than reducing information. So from this, what we can realize is that what exactly the network has learned. And secondly, we can also use early kernels and we can check how what the kernel exactly itself has detected to check the filters and the alignments that exist for our purpose. Now, for extensions, what we can also try is multi-scale course training, where we go from 32 to 16 to 8. Second, we also add energy-aware loss terms or constraints to check whether such models behave even better in uh, 2D Ising model scenario. Secondly, we can also check symmetries using enforcing spin flip or translational equivariance. Now, on this, certain limitations that our project kept was uh, that the finite size of our 2D IC model led to uh, led to the model being very easy for the model to learn. So if we go for higher or more complex systems, we might be able to see more differences that arise overall in this data. Secondly, there might be data biases as we only use from 0 to 4. If we go from beyond that, we might see newer effects in the system altogether. And also the boundary conditions that we have chosen is very simpler compared to what we can have chosen as well. Finally, moving on to this, what we have covered in this project, summarizing what we've covered in this project is that the educational value that we provide. So further extension and future work that we can look into are focus on critical regions, which further extension and future works that we can look into are model improvements, such as using the attention mechanism that is used in the current LLMs, or the residual connections, which can preserve fine-scaled informations altogether. That is, skipping a layer altogether and crossing information throughout that. Further, we can also add physical extension as well, that is trying out quantum spin systems, 3D Ising model, and different lattice systems altogether. With this, we demonstrate the intersection of machine learning and computational physics, and showing how neural networks can learn to perform sophisticated physical transforms that traditionally require an analytical understanding. This implementation follows both best practice for machine learning and computational physics, making it valuable and suitable for educational purposes while maintaining research quality standards. Thank you.